Okay, track 4 was kind of long. That was about 18 minutes. I don't like it to make them that long, but it's okay because you can pause it anytime you want and come back, remember where you were. I could do the whole thing on a Panopto type, but then I think the screen really sucks. It doesn't show up right, and the voice is bad. Now this is kind of screwy because I think when you call it, well, at least when I called up my solutions to the problems, this column here, which we're going to use for this geosynchronous satellite, and I'm just going to do this problem for you because I guess I've done them all for you, but I I struggled with this one a little bit because I didn't understand what the heck they were asking. I thought we were wanting to find like what would be a geosynchronous, but the moon doesn't rotate like the Earth does. Oh, thanks. So, in other words, what we're going to do is we're going to turn the moon. We're going to turn the moon into a satellite instead of it having it go around. This is its orbit, its period, and stuff. So, instead of using this for its period, we're going to go ahead and use. We're going to solve for r here. All right, is basically what we're going to do. Setting that equal to r cubed over t squared is equal to this. R cubed over t squared is equal to this. And then we're going to solve for t, but instead of putting a year, we're going to put a year in there, a year squared, but it's going to be what's the equivalent of 1 year in a in a day, because it's geosynchronous is one that for precisely 1 day. We're gonna find out what percent, in other words, what fraction 1 over 365 is what we're going to use is of the year is this. And basically all we're doing on this problem is this. This is all we're doing is we're saying, okay, and on the solutions, it's got 1.01 times 10 to the 18. It's actually 1.01 times 10 to the 19, which kind of screws things up. What they're saying is this. Based on Kepler's laws, which is not on your exam at all, we've got this relationship between the Earth and the Moon. As far as its satellite orbit. Kilometers to the what power? It's cubed over years squared. Okay? So that's what r cubed over t squared equals according. In other words, the period of the moon is 0.074 days. In other words, 0.074 years, which is 7% of a year, which is about 27 days. Okay? Because if I take 365, based on this table, I'm just showing you some astronomical data. This is all just general knowledge stuff. Okay, so if I take this table and take this number here and multiply it by 365.25, you get the period of the moon, of when every full moon that we get. All right, and I'm pretty sure I'm right on that. So I don't want to, 0.074 times 365.25. Yeah, 27.3 days. That's the period of the moon. But now we're going to treat using this constant here based on Kepler's laws. We're going to use this constant here and say, well, what if the moon was a geosynchronous satellite? What would be its R? Okay. I don't think we'd like it because I think it would be buried. The orbital radius. The orbital radius, remember, is r plus h, how high it is. Okay, and I think it would be buried inside the moon, but we'll see. All right. Oh, it's 10 and third class. No, it'd be very close. It'd be very, very close to the Earth. Okay. Because I was thinking of there's 6.38 times 10 to the 6th meters, but it's the radius of the Earth, just for general, is 6.38 times 10 to the third kilometers. Okay, and we're going to solve for r cubed here. We're going to see what it is, just compared to, we're going to solve for r and see how close it is going to be. Because right now the moon r is equal to 3.84 times 10 to the fifth kilometers. And so if I take r minus re, that's how I get the height of how far away from the surface of the Earth the moon is. And so if I take, I'm kind of giving you a little astro lesson here, and you're getting all the astronomy that I know. Second e to the fifth minus 6.38 second e to the third, and we get 3.77 times, okay, so it's still pretty high. I mean, it's 3.7762 times 10 to the fifth kilometers. Okay, so that doesn't take, see, since this is only 10 to the third compared to a 10 to the fifth, it didn't mess with it all that much. All right, so that's how high up, this gives me my height. All right, but now, so let's just go ahead and solve for this, but this time we're going to make the year. What is my year here? So I take r to the third, so I'm going to solve for r. So I'm going to take r cubed is equal to this constant k, which is 1.01 times 10 to the 19 kilograms cubed per year squared times t squared. Well, what's my period? In terms of a year, my period in terms of a year is going to be, 1 over 365 days in a year squared. And so r cubed is equal to 1.01 times 10 to the 19 kilograms cubed divided by, so this many years squared, divided by 365 squared. It's basically what we're doing. Okay, so let's plug that in. 1.01 second e to the 19. And for some reason on my solutions it said that was the 18. I'm going, no. Make me look like a fool again. 365 squared. Boom. I get 7.58. 1 times 10 to the 13 kilometers cubed. Take the cubed root of this, so I go second, so I go math, come down here, take the cubed root, excuse me, second answer. There it is. Oops, there it is. That's exactly right. 4.23 times 10 to the fourth. Yep. So take the cubed root of this. All right, so it's a lot closer now. What's up here? It's 10 times closer. Almost. All right, let's do the next one. Just call it a day. Okay. So it says a satellite of 500. Well, let's just take a look at it. All right. Just in case you don't believe me. Yeah, baby. All right, now, last but not least, here we go. Okay, Oh, this is just one. Okay, good. A satellite orbits the Earth at a distance of 198 kilometers above the surface of the planet. The radius of the Earth is 6.38 times 10 to the 6 meters, and the gravitational constant is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and the Earth's mass is 5.98 times 10 to the 24th kilograms. I was going to go into a whole thing because on your exam, if you've made it this far, on your exam, we talk about this equation here. And this is what we're going to be using for this problem, for problem 8 here. We're going to be talking about this equation here, where force is equal to G me, mass of 1 times mass of 2, divided by r squared. And that's what we're dealing with here, okay? All right, and that force is actually, when it's a satellite, is equal to MAC. That's the net force that's acting on it. This is Newton's gravitational. Now, you're going to get one conceptual question on this. So if you've listened this far, you're going to get the answer. All right, it says, what happens? What happens to the force on a planet, or on say you've got a rock sitting on Earth, okay, and it's got a weight of 15 newtons. Okay, so you got this rock sitting on the Earth. It's got a weight of 15 newtons. That we'll get to problem 8 here in a minute. This is more important. So I've got F then is equal to mg, which is equal to MAC, which is equal to this guy. And so the force is equal to G, mass of the Earth, mass of the rock, divided by r squared. Well, what happens if, what's the force it feels if the mass of the Earth becomes 4 times? So ME prime becomes ME 4 times ME, okay? And the radius doubles. RE prime now becomes RE, I should make this RE squared, 2R. What happens to this force? I want to make sure you understand how to square this. All right, so we'll just plug it in. F is equal to G times 4ME over the mass of the rock, which has not changed. The mass of the rock still stays the same, divided by RE squared, which is 2RE squared. Well, look at this. That is G is equal to 4ME MR over 4RE squared. Look at that. Nothing happens. Still equals 15 newtons. All right. Well, let's just look at the geosynchronous satellite in the next video.